First up, we've got Rory Smith, known, I think, to most here. Rory is currently working as a consultant with Peter's research. The gravitational pull in that direction seems quite significant. Essentially, Rory, you're going to talk to us about electromagnetic compatibility. So, over to you.
Yeah, I first became associated with electromagnetic compatibility about 25 years ago when I had to get I was working for computerized elevator control who made the Swift Futura controllers, and we were selling them in the UK, and we had to get the CE label for it. In order to do that, we had to pass the electromagnetic compatibility testing. And I was also involved in after ThyssenKrupp bought Dover Elevator, I did some electromagnetic compatibility work for them. But in 2008, I got transferred to Dubai to set up their service operation in the Middle East. And it kind of didn't exist. And part of the service organization's responsibility was essentially to finish the installations. Now, that's not unique to Dubai. That's a lot of places that happens. And so what we ran into was a tremendous amount of electromagnetic problems because the buildings were so tall. And because a typical building there at that time was 50 floors, 60 floors, and you had very large drives because the minimum speed was 3.5 or 4 meters per second. So you had big drives, big long wiring, and so I became associated with. So what I'm going to talk about is what I've learned the hard way about electromagnetic compatibility, and I wanted to share it. So electromagnetic compatibility is also called EMC. So people use it interchangeably, and it really consists of two significant components. And one of them is emissions. Emissions are the electrical noise that the lift system makes that can interfere with other equipment. And that's covered by BSEN 12015. Will be converted over to an ISO standard shortly, I believe. And then there's also immunity, which means you want to make yourself immune to noise coming in from other sources. And that's covered by BSEN 12016. Now, how do you test a controller for this or any other lift equipment? Well, they use these things are called anechoic chambers, and they're used for testing EMC. And essentially what you do is you put your part where that table is, and then they have these various antennas, and you listen to the noise coming from the controller, and it has to be over a very wide frequency range, and it has to be below a certain intensity level, the noise you're making. They also connect transformers up to the three-phase power line, and they look for noise that's conducted across the line. Then they turn on a transmitter, and they try to nuke the controller with high-powered radio frequency. And it's done inside these chambers so that it doesn't radiate and interfere with the other equipment outside, and so you don't receive any interference from outside. But what you don't see in these chambers is how long are things like traveling cables and how long are hoistway wiring. Well, for the purpose of these tests, they're 5 meters long. 5 meters. It's next to nothing, and that's the test. But then here's a picture of a setup for the test. And so it shows, like, number 6 there are 3 hall stations, but 5 meters of wire. And the traveling cable, the car is 5, I believe, and so from 2 to 5 is the traveling cable, again, 5 meters, not representative of the real world. And so the standard says, well, you have to have a set of instructions that tell you how to install this. I know they exist, I've never seen them, never in the field. And so most everything in the Middle East at that time was installed by unsupervised contractors. And when you're using subcontractors, you better have more supervision than you have with your own forces, or you get nothing. Because you don't get what you expect, you get what you inspect. And you don't inspect, you don't get anything. So noise controllers, electromagnetic interference is what we're really dealing with. Compatibility is just the name of the standards, and that's what we want to be: good neighbors and not broadcast interference to other people. And we want to protect the safety of the elevator by having a good immunity. So controllers, essentially it's electrical noise, and controllers don't like noise because it interferes with what they're doing, and humans don't like acoustic noise. So how do you deal with a noisy neighbor? Well, you control the emissions, so you stop the noise at its source, and so and how do you make yourself immune to noise? You block the noise with headsets, things like that. But we're doing something similar electronically. So what often happens is lift controllers interfere with themselves, and so what we need to do is we need to muffle the noise sources in our control system, and we need to block the noise from noise coming into the system from the external. So to understand how to control EMI, electromagnetic interference, we need to have an understanding of what interference is. And there are four basic types of electromagnetic interference. There's inductive interference, capacitive, radiative, and conductive. Those are the four major sources. So let's take a look at, here's a diagram that shows a little bit of everything. You can see there's the source there, and some of the noise is inducted across those coils, some of it is conducted by wiring, some of it is connected by capacitance to the victim, and then there's also the part that's radiated. So these are the four sources. And so let's take a look at how that works with inductive coupling. With inductive coupling, we think of a transformer. And when we think of capacitive, we think of just capacitors. And that's really what they are. And with radiative, we're looking at antennas and things like TV towers that radiate a lot of energy, but we have cell phones everywhere. We have mobile radios. All of these are potential sources, and then we have conducted. And this is just conducted across through the three-phase lines into the system. So these are these sources here. Inductive only works with alternating currents, and these alternating currents exist in the 50 hertz wiring that you have in your home or in your office. But electromagnetic interference always has an alternating source. But radio frequency interference is an alternating source, so it functions just like the power in your house. So, what can we do? How does this work, and how can we mitigate it? Well, here's an inductive circuit. So you have a primary coil, and you have a secondary coil. And if you complete the circuit with an AC generator, you'll get energy that will transfer across the coils and into the circuit. Very, very basic. So now, when we have inductive coupling, if you move the two coils together closer, you'll get more power across the circuit. So the concern there is that we can get induction with straight lines, with straight wires. So it doesn't have to be a coil, just straight wires like the straight wires in a traveling cable or the straight wires in a hoistway cable, the wiring cable. They can be sources of induction. And so if we complete the circuit, we will get some energy transferred across this circuit. Now, the longer the wires are, if we make them longer, we have longer, in effect, coils or surfaces that can transfer the energy. And so we'll get, think of hoistway wiring. The longer it is, the more likely we are to inductively couple across these wires. So we were showing here an electrical source, but it could be a noise source. The noise source could be anything that makes noise. Somebody welding next door. It could be other lift equipment, and so we will induce noise into the secondary, just like it was a a transformer coil. If we move the two wires further apart, we'll find that we get less power is induced. And so this is known as separation. So one of the ways to mitigate this is to just move the wires further apart. If you do that, and we'll go into how that's done practically, but we do that, we can reduce the amount of noise we get. There's less energy if we put shielding. So if we shield one side of this, we're not going to transmit as much energy. If we shield the other side, we'll get even less energy transmitted. So this is shielding. So the two real methods to solve this are separation and shielding. So we've just reviewed inductive, but there's the capacitive, and all the methods that we have, capacitive, inductive, and are all controlled the same way by separation and by shielding. So those are the methods that they both work. Now, with capacitive coupling, we have like two capacitor plates. These can be two wires in a hoistway, and if you have a noise source, complete the circuit, you can actually, through capacitance, transfer the energy to the other plate. Just like in capacitive theory, if you move these plates closer together, well, you're going to get, or further apart, you get less. If you move them closer together, you get more energy transfer. If you move them further apart, you get less energy transfer. So again, separation works, and so shielding also works well. Now, what are some example of components with significant amounts of emissions? Well, VVVF drives are a big source of emissions, and the larger the drive, the larger the emissions, and also the higher the carrier frequency, or also referred to as the chopping frequency, the higher the switching transients. And so, if initially some of the early inductive or VVVF drives had a switching frequency of 3 kilohertz. Now today, 10 kilohertz is standard, and some people even go up to 16. The higher the frequency, the smoother the sine wave coming out of the drive, but also the higher the switching transients, and the more problem they can solve. So, higher the frequency, the larger the emissions. So let's take a look at some practical examples. Here we have a machine, a drive, and we've routed the encoder wiring next to the power wiring to the motor. Now that's a good way to induce or couple interference into the system. And so, what can you do when you have a situation like this? Well, the drive is making noise. The solution is separation, which we can reroute them and further apart. That works. But we can also, the minimum separation is 200 millimeters. So not that far. The further, the better. And then if you want, you can add shielding, and that's the best solution, because then you put them in conduits or troughing that's earthed, and you will greatly reduce or eliminate this problem. Now, there's two words for earthing. One is grounding and one is earthing. They mean the same. Grounding is the U.S. and Canada, and earthing is the rest of the world. But they're just used interchangeably. So we can shield them, and there's other ways to shield. Oh, I'm going backwards here. There's other ways to shield, and this is a standard cable that you'll see in most of Europe, where you have the three-phase conductors and an earthing conductor, and they're all together, but they're within a braid. There's a braided shield around the outside of them, so that keeps the noise from getting out. So let's take a look at shielding and separation and which one works better. So here we have high power cables and we have low power cables, and if we keep them 200 millimeters apart, we reduce the coupling. And so that's a good approach. A better approach is to put them in a shielded troughing. Now, what that does is it's better because it has good separation, but it keeps noise coming in from the outside. But there's a better solution, and that's if you have a troughing with a divider in the middle, then you really you have both shielding and separation. So good shielding, separation really isn't required because it's there. And then using 2 shielded cables also works extremely well, and that's what most people are doing in the real world. It's important to understand with radio frequency and alternating current circuits, most of the energy it goes through the skin of the cable, not through the core. It's called the skin effect, and that has a lot to do with how you connect the shielding. Now, if you think about high power wires that you see on poles, they're typically made out of they're steel cables, and only the outer layer is copper. Now this because the inner part isn't really conducting even at 50 hertz very much energy, and the steel also keeps the cable from sagging and the copper from stretching out. And it's in certain radio transmission facilities where they have high power, and they use copper tubes, like copper plumbing tubes are what the conductors are, because there's absolutely no energy going through the core. But where this comes into effect is how do we terminate our shielding? And so here's an example, and you see here these cables have been physically mounted right here. They're mounted, and they're strapped to the insulation. And then you can see, if you look, you can see that there's the shielding the insulation has been removed from the shielding. And then what you're supposed to do is, what we see in this picture here, notice how you have a clamp that goes all the way around the shielding. And what that does is it takes advantage of the skin effect, and it gives you the most direct path to the earth or grounded controller frames. This is the right way to do it. Not always done. In fact, more often than not, from what I found, it wasn't done. And so here's an example where they strip the shielding off of the cable, make it into a pigtail, and then run that and attach that to an earthing lug. It's called a pigtail, and in reality, pigtails are a very good antenna, and so they broadcast. So you're not supposed to do that, but it's done all the time because people think in terms of continuity. Well, I've got 0 ohms here, it must be really and it's good for resistance and DC, but for AC it's quite different, and for radio frequency it's quite different. And this is typically not well done. So I have some other examples of connections that were not quite done right, but we'll just take a look and compare one more time. Here's the pigtail, and here's how it should be connected with. This looks like even like a conduit strap, and that's a very common way to strap these down. As long as it grabs the entire shield, then you're going to get it's going to work well. So that's the incorrect. That's the correct, and so here's another type of shielding that is very common on motor shields. It's a gland seal, a gland connection. And these, you see, the shield is folded back. When you put these together, the entire shield is attached to, in effect, the motor, the body of the motor, and everything is grounded. So this is an effective system. Now I'm going to show you some samples of things that weren't quite right. And this looks like it's very well wired. These are photos, the light curtains. And what you have is the green and yellow earthing conductor, and it goes right here and it's screwed into the door. Okay, it looks like it should work well, except they didn't scrape the paint off the door. And so now you have good continuity, but you don't have good contact for radio frequency. So you have to take some sandpaper or something and scratch all the paint off, and then put the ring lug on, and then tighten it up, and then you have a good solid earthing. Here's another practice that I've seen this on like giant gearless machines. They have a grounded lug, but the whole thing's painted, and they mask off the stud with the threads, but they didn't take the paint off below, and then it really you get some effect, but you don't get the right effect. So here's an installation where of troughing in a machine room, and they put these little twisted wires between the segments of the troughing. Well, it's from continuity perspective, it's good, but what those are is coils. And so never make a coil, because then you now have an inductor, and it's a little bit different. What really works better is to use, if you're going to do that, a braided shunt, because again, it has a lot more surface area. With all the little wires have the overall surface is much larger, and it gives you a good solid connection. Also, the couplings where the parts are screwed together need to be as good as you can make them, because all of this makes it a better earth device. So here's a variable frequency drive, and what you can see in this picture here is that the encoder low power wiring is strapped to the high power wiring. This is absolutely what you want to avoid doing, because that will create a lot of interference. If the wires have to cross, they need to cross at 90 degrees, so that you have the minimum amount of conduction and induction. So if we look at this one, what we've actually got here is that we had excess cables, so we made it into a transformer coil. And so it's a loop back and forth, and this this has to be fixed. What's the date on that? 2010. That was when I was in the Middle East, and basically what we ended up doing was everything was built in a big rush, and we had to set up a training class, and we had classes going daily to train people in this type of issue, and installation and maintenance, because the people wanted to learn, they were capable of learning, but no one had ever taught them anything, and they just did whatever they could do to get the things installed. So looped wire makes a coil, improved induction. Here's a real disaster. This is a variable frequency drive. The high power cables are fastened to low power cables. The drive location makes it very hard to adjust or replace up behind the governor. And then the drive and resistor box location, these are the dynamic braking resistors. All the heat will collect at the top of this machine roomless application. And the heat from the drive and the heat from the resistors, and it's bad for both. It's just a bad installation. It had to be really ripped out, and we started over. And the resistor wire is just joined right here, and it just uses black tape. Well, the voltage that you have with high frequency switching is much higher than the normal voltage, and this is probably not a good insulator at all. You shouldn't do things like that anyway, but yeah.
Grab hold of it, it'll probably
Kick you. Yes. Well, this next one, the next picture here is a real picture. Do you see anything you like? Kind of an interesting story. The man here that's holding this, these are encoder wires, and they were joined together inside the troughing, and then they used masking tape as insulators. Then you see there's these black flexible conduits. Well, actually, you can always, if you want to, run a flexible steel conduit inside a troughing, because it gives you good insulation. These happen to be plastic, so they have no insulation whatsoever. There's a nice way to keep the wires physically separated, but only by a millimeter. But it was just a complete disaster. So we had to completely rewire this and separate the high and low voltage. You never want to make terminations inside of a conduit or a trough, because it's just bad practice, and it adds for a lot of troubles. There's also a lot of misinformation floating around on how to do EMC. And one of the ones that is a lot is shielding terminations. And you have an analog expert, and the analog expert says, only connect the shield to earth at one end of the cable. Well, that was true with analog. When you had 10 volt, 12 volt tachometer, DC tachometer encoders, that was the right thing to do. But That's not the right thing to do now. So a digital expert will tell you, always connect the shield at both ends. But a lot of people are still connecting them at one end. So my advice is listen to the digital expert, because we're not, unless you're dealing with an older system with a DC and a DC tachometer, you want to shield both ends. People say, oh, well, if you shield both ends, you get ground loops. That's true if you were in the analog world, but we're in the digital world, and it's completely different now. So we also have to deal with radiated interference. And so there's everyone has walkie-talkies on job sites. Everyone's using mobile phones on job sites, and that's radiated interference. Here's an airport. Airports are particularly noisy, but because you have, this is an instrument landing system, and that's the main antennas across here are log periodic antennas, and they are in the 110 megahertz range. And then the man's holding a 75 megahertz fan marker beacon antenna. So you have these, and then you have the glide slope antenna, and then you have the aircraft communication radios. And so airports are a good place to run into, I found it to be a good place to run into a lot of EMI issues. The other thing you have is with radiated interference is if you're near sources of like TV towers, like the BT tower in London, you're going to get a lot of energy. How do you handle it? Well, this can be handled quite easily. Close the cabinet door. And that makes a great shield. It'll also, people say, well, I need to open the cabinet door for better cooling. No, actually, that's not true. You get better cooling with the door closed because the air comes in, is designed on the cabinets to come in the bottom, through convection, go out the top, and you get better chimney effect if you keep the doors closed. So keep the doors closed for cleanliness, keep it closed for cooling, keep it closed for radiated interference. EMI noise can cause intermittent problems. And that's how you detect that you have a problem, is you get these ghosts, you get these phantom trouble calls that appear. And and many times the lifts are interfering with themselves. So the phantom calls appear, phantom calls cannot be explained. There's no, the car's shut down, but you just cycle the isolator switch and all of a sudden it runs, and you think, well, it's fixed. And then the customer gets dissatisfied, because there are also safety issues, but there's a lot of these issues. One of them that I was involved recently with an airport, and they had 150 escalators, and they were about 10 years old. And they on average, each escalator would shut down 2 or 3 times a week, and they'd go, and how did they fix it? They cycled the isolator switch. And it was never a skirt switch or a step loose comb plate switch. None of the safety switches were tripped. It was just, all you had to do was cycle the disconnect switch and it ran. And so one of the things that we discovered with this is that it was previously unknown problem. There's component aging that occurs. And it occurs in these EMI filters. And they age over time. And also, metal oxide varistors, basically every time there's a transient, it burns a little hole in the thing, and pretty soon it's full of holes, and there's no more that it can't absorb any more energy, and they need to be regularly replaced. And the same is true with the main EMI filters. You see these on the line side of variable frequency drives in Europe. Not required in the U.S. or Canada, but it's a good practice to do it. And what happens with these filters is that they're between, you have the filter, this is the incoming power, you have the filter, sometimes you put an inductor in here, usually not, and here's the drive and the motor. And so these keep the noise from the drive from going out, but they also keep any noise that's coming in. They'll eat the noise coming and going, so they're very effective. However, you notice that here's a circuit diagram. These are referred to as LRC networks because the coils are labeled with an L, the resistors an R, and the C is the capacitors. And what happens is the capacitors age over time. And so if you check with someone, Schaffner, the people that make a lot of them in Switzerland, they'll tell you they're only good for 10 years. But nobody's ever changed one that I've known. And so this particular airport had 150 12-year-old escalators with filters. They had 2 filters. They had an LRC filter, 3-phase, and they also had the control. Actually, the controller was a PLC, and then they had a little filter in front of the PLC as well. And both of them needed to be changed because they were both over 10 years old. And so you can.
How are we doing? I think we're running out of time.
I'm wrapping it up. So, so here's the circuit with the MOVs, and again, you have to replace the MOV. And so EMI is a big problem in tall buildings and buildings over 10 years old. Questions? Yeah.
Is that working? Can you hear me? Oh, good, yes. Rory, thank you very much. That was a masterclass.